Hello class, this is Fire Service Hydraulics and Water Supply, Chapter 11, Fire Hose Nozzles. Once this lesson is completed, you will be able to identify the functions of solid stream, fog, and broken stream nozzles, as well as demonstrate how to calculate nozzle pressure and reaction in various types of nozzles. I'm going to list all of the learning objectives we're going to cover in this chapter, and they are as follows. Once this course is completed, you will be able to identify the functions of solid stream nozzles in the fire service. Objective 2 will be to identify the functions of each type of fog stream nozzle in the fire service. Objective 3 will be to identify the functions of each type of broken stream nozzle in the fire service. Objective 4 will be to demonstrate how to calculate nozzle pressure and nozzle reaction in various types of nozzles. And we're going to start now with learning objective 1, which is to identify the functions of solid stream nozzles in the fire service. There are three basic types of fire streams used in manual firefighting operations. They are solid stream, fog or spray stream, and broken stream. Producing each stream requires a specific type of nozzle, and there's no nozzle that can develop both a true solid stream and a true fog stream. And I'll clarify what that means as we proceed. Most fog stream nozzles can produce a straight stream that has similar properties to a solid stream, but it's not a true solid stream. Most fire apparatus are equipped with a variety of different nozzles to be used depending on needs at the incident. Operators should understand which size and type of nozzle is appropriate for the incident at hand. Once that determination is made, you must know the nozzle's operational principles, including how much pressure the nozzle needs to operate efficiently. Varying correct nozzle pressures for each type of nozzle will affect the pump operator's hydraulic calculations. A handline nozzle is any nozzle that's designed primarily for attachment to a single movable hose line and manual control in operations by one or more firefighters. IFSA limits the maximum amount of water that can be safely flowed through a handline nozzle to 350 gallons per minute or 1,400 liters per minute or less. Now we're going to talk about master streams. A master stream is designed to be located and operated from a specific location and to flow large volumes of water beyond that which firefighters could control manually. IFSA identifies any flow above 350 gallons per minute or 1,400 liters per minute. IFSA also clarifies any flow above 350 gallons per minute or 1,400 liters per minute as a master stream application.
Most common flow capacities of master streams used by municipal fire services range from 500 to 1,000 gallons per minute, which is 2,000 to 4,000 liters per minute, although some municipalities do have higher capability. There are specialized applications that use master stream nozzles capable of flowing up to 20,000 gallons per minute or 80,000 liters per minute. Solid, fog, and broken stream nozzles are all available in both handline and master stream designs. Let's talk about solid stream nozzles. This is the oldest style nozzle used by the fire service. It is designed to produce a stream as compact as possible with little shower or spray. It may be used on handlines, portable apparatus mounted master streams, or elevated master streams. The design of the nozzle is extremely important in producing the desired compact fire stream.
While development of these nozzles proceeded, there were a set of experiments called the Freeman experiments. These experiments compared streams from different types, kinds, and sizes of nozzles. They tinkered with various designs, specifically Mr. Freeman, until he finally found a nozzle shape and design that produced an optimum stream.
Freeman's design, known as the standard tip, remains the basis for solid stream nozzle design today. Solid stream nozzles are designed to gradually reduce the shape of the water in the nozzle until it reaches a point near the outlet. The nozzle becomes a cylindrical bore whose length is from 1 to 1 and 1.5 times its diameter. The cylindrical bore rounds the water before discharged, and a smooth, finished waterway contributes to both the shape and reach of the stream. Alteration or damage to the nozzle can significantly alter the stream shape or performance. The majority of fire services believe that solid stream nozzles on handlines should have a discharge diameter no greater than 1/2 the diameter of the hose to which they are attached. Many fire departments do equip a 2.5-inch or 65mm handline with a solid stream nozzle whose tip exceeds 1.25 inches or 32mm. And also, many fire departments learned that a 2.5-inch or 65mm handline can be equipped with a solid stream nozzle whose tip is as large as 15/8 inches or 42mm without reducing the quality of stream. Handlines attached to high-energy compressed air foam systems, or CAFS, are routinely equipped with nozzle tips equal to the hose line's diameter with little loss of effectiveness. A standard solid stream nozzle has a fixed discharge tip diameter. This is particularly true of solid stream nozzles designed for use on smaller 1.25 to 1.5 or 32 to 38mm handlines. These are the only ways to lower flow from nozzles that are designed for use on smaller handlines, and that is to reduce the pressure of the water being supplied to them or partially close the nozzle valve. There are larger handlines, and most master solid streamline nozzles are equipped with stacked tips, as you see illustrated in the picture here. Stacked tips are a series of threaded nozzle tips whose diameters decrease as they extend from play pipe to tip. The most common is the 2.5-inch handline stacked tip nozzle and has a play pipe with 1.5 inches or 38mm tip, to which 13/8, 1.25, and 1 inch, which are 35, 32, and 25mm tips, are added. Before opening the nozzles, firefighters select the diameter of the tip based on the conditions they face and available water supply. Stream velocity, or nozzle pressure, and the size of the discharge opening determine the flow from a solid stream nozzle. As either or both increase, so does nozzle flow. Both velocity and discharge opening size do have limitations. There are practical limitations on the amount of nozzle pressure that can be supplied to a solid stream nozzle. When a solid stream nozzle is used on a handline, it should be operated at no more than 50 psi or 350 kilopascals of nozzle pressure. Above that, nozzle reaction on hose line may become too great for firefighters to actually control. Most solid stream master stream devices should be operated at a nozzle pressure no greater than 80 psi, which is 560 kilopascals. The operating portable master stream device above 80 psi or 560 kilopascals may cause excessive nozzle reaction. This excessive nozzle reaction may cause portable master stream devices to move and endanger personnel working on scene. Operating an elevated master stream nozzle at an unsafe pressure may place excessive stress on an aerial device. It may damage the water system, dislodge the detachable master stream nozzle from the ladder, or damage the ladder itself. For special situations with solid stream nozzles, some solid stream master stream nozzles may be designed to operate at a discharge pressure in excess of 80 psi or 560 kilopascals. These nozzles connected to a fixed piping system in industrial facilities exist, and these also exist as large nozzles on fireboats. They're specially designed deluge fire apparatus. Deluge fire apparatus with larger master stream nozzles may be equipped with outriggers to help keep the apparatus from moving when the nozzle is being flowed at high pressures. When using these specialized nozzles, be familiar with the operation and make sure to not exceed their design safe operational limits. The procedure for determining flow volume for a solid stream nozzle is what we're going to discuss now. There is a specific procedure, and it works for solid stream nozzles of all sizes. It can be calculated fairly closely if equipment used to measure the nozzle discharge pressure is accurately calibrated. It's essentially the same as determining flow from a fire hydrant discharge opening. So to do this, insert the pitot tube and gauge into the fire stream at a distance from the tip equal to 1/2 the diameter of discharge opening to get accurate reading on discharge pressure exiting the nozzle. If you'll notice in the picture, it looks just like when you were using that same device to measure the flow rate from a hydrant. So the formula to determine the flow from a solid stream nozzle is a simplified version of the formula used to determine flow from hydrant discharge. Because the design of most solid stream nozzles is very similar, a standard coefficient of discharge is factored into the equation. So here's the equation. It is 11.1 in your text, and it's a flow from a solid stream nozzle in gallons per minute equals 29.7, which is our constant, times the diameter squared times the square root of NP, which is your nozzle pressure. This is it in metric. It's the same formula, it's just that your value of your constant is going to be different, and ultimately the value of the numbers you plug in will be different. But it's liters per minute, not gallons per minute, equals 0.067, which is your constant. D is the nozzle tip diameter in millimeters, and NP is the nozzle pressure in kilopascals. So here's an example of determining flow rate for solid stream in US customary or imperial measurement. In your example, it says determine the flow volume from a 1 1/4 inch solid stream nozzle tip operating at 50 psi. If you look under solution, the first line is your formula again, gallons per minute equals 29.7, which is your constant, times diameter of the nozzle tip squared times the square root of NP, which is your nozzle pressure. Gallons per minute equals 29.7 times 1.25 because it's 1 1/4 inch squared times the square root of 50 because your nozzle pressure is 50 psi. That gives you gallons per minute equals 29.7 times 1.5625 times 7.07 gives you gallons per minute of 328. Pretty straightforward. Here's your example in metric. The example is to determine flow volume from a 32 millimeter solid stream nozzle tip operating at 350 psi. And under the solution, you see the first line, liters per minute equals 0.067 times diameter squared times the square root of nozzle pressure. That's your formula. Again, you're looking for liters per minute, not gallons per minute, and your constant is 0.067 in metric. So in the next line, you plug in your values. Liters per minute equals 0.067 times 32 squared, that's your diameter of your nozzle tip, times the square root of 350, which is your PSI. Liters per minute, if you factor everything out in the next line, equals 0.067 times 1024 times 18.7. Again, when you multiply it all out, that gives you liters per minute equals 1,283. Here's another example. In US, A detachable ladder pipe is attached to an aerial device and it's equipped with a solid stream nozzle having a 2-inch nozzle tip. The nozzle is now being operated at a discharge pressure of 80 psi. What is the flow volume being discharged from that nozzle? Works exactly the same as it did before. Gallons per minute equals 29.7 times diameter squared times the square root of nozzle pressure. If you plug in your values, you have gallons per minute equals 29.7 constant times 2, because it's 2-inch nozzle tip, squared, times the square root of 80, which is your pounds per square inch being discharged through the nozzle pressure. And it gives you on the next line, gallons per minute equals 29.7 times 4 times 8.94. And when you multiply it out, it gives you gallons per minute of 1,063. Here's the next example in metric. A detachable ladder pipe is attached to an aerial device and is equipped with a solid stream nozzle having a 50 millimeter nozzle tip. The nozzle is being operated at a discharge pressure of 560 kilopascals. What is the flow volume being discharged from that nozzle? It works just like it did before. Under the solution, you have your formula, liters per minute equals 0.067 times diameter squared times the square root of nozzle pressure. And on the next line, you plug in your values. Liters per minute equals 0.067 times 50, it's a 50 millimeter hose tip, or nozzle tip, squared, times the square root of 560, because you've got a nozzle pressure of 560 kilopascals. Next line, you just factor everything out. Liters per minute equals 0.067 times 2500 times 23.7. And on your last line, after you multiply everything out, you get liters per minute equals 3,970. Okay, class, here are some questions for you, review questions. First, what factors determine the flow from a solid stream nozzle? That will be on page 252 of your text. Next, when a solid stream nozzle is used on a handline, how much nozzle pressure is allowed before it becomes too great for firefighters to control safely? That's on page 253 in your text. Learning objective 2 will identify the functions of each type of fog stream nozzle in the fire service. Most flexible nozzles available to the fire service are fog stream nozzles. They're sometimes referred to as spray nozzles, although honestly I've never heard them referred to that way. Generally everybody calls them fog nozzles. These allow firefighters to carry a variety of streams that each have their own uses and advantages. In general, straight streams and narrow fog streams are used for aggressive up-close firefighting operations. Wide fog patterns are most commonly used to protect exposures and firefighters from high levels of radiant heat. Fog stream nozzles do not have an unobstructed waterway through the nozzle. They use a mechanism to break the column of water into a series of droplets as it travels through the nozzle. The column of water is driven against the obstruction with sufficient velocity to shatter the mass of the water overall. The angle at which the obstruction deflects a stream of water determines reduction in the stream's forward velocity, and pattern and shape stream assumes the appropriate shape based on the deflection. Wide angle deflection produces wide angle fog pattern. Narrow angle deflection produces a narrow angle fog pattern. Most modern fog stream nozzles use periphery deflection. These are produced by deflecting water from the periphery of inside the circular stem in the nozzle. The exterior barrel of the nozzle deflects this water before it leaves the nozzle. The relative positions of deflecting stream and exterior barrel determine the fog stream's shape. This gives you an example of how this works. This is rotary control valve operation, a fog stream pattern, and you see the deflection stem inside. And you see how it's set one way in the top illustration and produces basically two triangular fog patterns. On the bottom, you see where the deflection stem is in farther, and it produces basically columns of water droplets. Early fog stream nozzles used impinging stream nozzles. They drove several jets of water together at a specific angle, breaking the water into finely divided particles. These produced very effective quality wide fog streams, but less effective narrow fog patterns and straight streams. Impinging stream nozzles are rarely used in the fire service today. This is an example of an impinging stream nozzle. The advantage of fog nozzles is that when water is discharged at angles to the direct line of flow, reaction forces tend to counterbalance each other, thus reducing nozzle reaction. This is why fog patterns are easier to handle than solid or straight stream patterns at the same nozzle pressures. Most modern fog stream nozzles are designed to operate at a nozzle pressure of 100 psi or 700 kilopascals. Operating a fog nozzle at discharge pressures lower than this will impair the fire stream from every single type of fog nozzle. Fog stream nozzles come in a specially designed low pressure fog stream nozzle, and it's designed primarily for high-rise firefighting, and that is the one exception to that rule. It may be difficult to get sufficient pressure to upper stories of very tall buildings in order to supply fog stream nozzles with 100 psi or 700 kilopascals. But these are specially designed nozzles so they can handle that lower pressure. But any of your other standard nozzles definitely don't need to be below 100 psi. Low pressure fog nozzles that we were just discussing are designed to have effective stream patterns and safe flow volumes at nozzle pressures of 50 to 75 psi or 350 to 525 kilopascals. Though originally designed for high-rise fighting, many fire departments are using them in everyday standard firefighting situations. These allow firefighters and apparatus to deploy effective fire streams with less nozzle reaction and lower pump discharge pressures. So you may find yourself using this kind of low pressure nozzle in everyday work. The fire service uses several basic design types of fog or spray nozzles. Each has its respective place in the fire service. You need to understand the basic principles of each type of nozzle to be able to select the best for any emergency situation. Now let's talk about variable flow nozzles. This is the earliest fog nozzle design, and it produces different flow volumes depending on the particular variables of each fog nozzle, variable fog nozzle design. These variables include stream pattern, water pressure supplied to the nozzle, the size of the supply line feeding the nozzle, but few of these are in service today, but in a volunteer fire department or an older department you might still see them. There were two basic fog nozzle designs that used a periphery deflected stream. One type was turned on and off by means of a ground seat within the nozzle barrel. The water would flow in a wide pattern fog when the nozzle was first opened. The second type contained deflection stem that fit the ground seat at the orifice of the exterior barrel. Water would flow in a straight stream when the nozzle was first opened. Both styles of rotary control nozzles have variable flow volumes depending on the stream pattern selected. The flow volume from rotary control nozzles is greatest when the stream pattern is widest. Some nozzles are capable of near 90-degree fog patterns. The flow volume decreases as the fog pattern is narrowed. The flow volume is lowest when the nozzle is set at the straight stream. The flow volume may decrease as much as 50% when the wide fog pattern is changed to straight stream. There are also variable flow nozzles dubbed or nicknamed mystery nozzles. These are variable pattern nozzles with a ball valve shutoff that also used periphery deflected streams. The discharge changed each time the fog stream pattern changed. This mystery nozzle used to receive flow volume rating at 100 psi or 700 kilopascals nozzle pressure using a narrow fog stream of about 30 degrees. If 100 psi or 700 kilopascals of nozzle pressure was maintained and the pattern then changed to a straight stream, flow volume was decreased approximately 15%. If the pattern of the stream changed from straight stream to the widest possible fog pattern, flow increased approximately 15% when that happened. Constant flow nozzles is what we're going to talk about now. While variable flow nozzles may place firefighters in a dangerous situation of having insufficient flow to safely extinguish the fire or protect themselves, the earliest solution was to develop a nozzle that could maintain the same flow volume regardless of the stream pattern setting, which became a constant flow nozzle. Constant flow nozzles flow a specific amount of water at a specific nozzle discharge pressure on all stream patterns. Most utilize a periphery deflected stream. As exterior barrel is rotated to change fog stream pattern, the space between the deflecting stream and the internal throat remains the same. As a result, the same quantity of water passes through the nozzle. Early constant flow nozzles were rated for a single flow volume of 100 psi nozzle pressure or 700 kilopascals. Different situations called for different flow volumes. This resulted in refinement of the constant flow nozzle. Refined constant flow nozzle has a number of constant flow settings, enabling the firefighter to select the flow rate that best suits conditions. The nozzle supplies selected flow at rated nozzle discharge pressure. If the pump operator cannot supply proper pressure, actual flow will differ from that's indicated at the nozzle. This gives you an example of constant flow nozzle, 100 gallons per minute or 400 liters per minute. It's adjusted to be as much of a straight stream as possible. Then here you've got still at 100 gallons per minute, you got a narrow angle, which is a 30 degree, and a wide angle, which is 60 degree. So the the constant flow nozzle gives you the same amount of water no matter how you adjust the spray pattern. Both constant flow and adjustable constant flow nozzles have proved highly reliable. There are many original models that remain in active service. Most nozzle manufacturers continue to produce updated versions. Constant flow nozzles solve some important problems but also had their own problems. If the pump operator fails to supply the rated nozzle pressure to the nozzle, the flow volume will be less than the nozzle rating and a stream pattern's quality may end up being unsatisfactory. If the pump operator supplies too much pressure to the nozzle becomes unwieldy and poses a physical hazard to firefighters attempting to handle it. So this brought about the advent of constant flow volume or automatic nozzles. These were created to make up for the deficiencies of the constant flow nozzle. These maintain a constant nozzle pressure of approximately 100 psi or 700 kilopascals, no matter how much pump discharge pressure is above this figure. With an automatic nozzle, a baffle moves automatically, varying the spacing between itself and the throat. As the pump discharge pressure increases, the nozzle automatically enlarges its effective opening size within the nozzle's range to match the flow. You see an example of that here on the slide where it says slide valve operation. Automatic nozzles do not provide constant flow volume under all conditions. If pressure and corresponding volume supplied to the automatic nozzle increases or decreases and the nozzle pressure remains at 100 psi or 700 kilopascals, the nozzle's flow volume will change accordingly. Automatic nozzles allow pump operators some safety to err on the high side of supplying hose streams. If the operator supplies too much pressure to constant flow volume nozzles, the nozzle pressure resultant reaction can increase to dangerously unmanageable levels for the hose team. If the operator supplies too much pressure to automatic nozzle, the nozzle pressure remains at 100 psi or 700 kilopascals and the nozzle reaction remains constant. Flow volume being discharged may actually end up increasing. If a pump operator is not supplying minimum rated pressure to automatic nozzle, the stream pattern can look good but may not be discharging sufficient water for extinguishment or firefighter protection. The automatic nozzle may allow pump operator to supply too much water to the nozzle and exceed incoming water supply. If the pump approaches the point where it's trying to discharge more water than it's taking in, the engine will start to speed up or become erratic. The intake supply hose will become soft or begin to collapse. Intake pressure gauge may be at 0 psi or close to 0 psi or kilopascals. The pump operator should back off the engine throttle until the intake pressure gauge reads at least 10 psi or 70 kilopascals and preferably 20 psi, which is 140 kilopascals. Otherwise, the pump may go into damaging cavitation condition. Some review questions. In what situation would it be advantage to use wide fog patterns from a fog stream nozzle? That's on page 256 of your text. Next question. What is one advantage of using fog nozzles? That's on page 257 of your text. Next question. What are two disadvantages of using automatic nozzles? That's on page 263 of your text. Learning objective 3. Identify the functions of each type of broken stream nozzle in the fire service. Broken stream nozzles force water through a series of small holes on the nozzle's discharge end. Broken streams produce larger droplets of water than do fog streams, which tend to give them a better reach and penetrating power. Broken stream nozzles almost exclusively are special use nozzles for use on chimney fires, basement fires, or fires in inaccessible spaces. The decision to carry these nozzles is typically based on experiences of a particular jurisdiction, the types of fire situation it commonly encounters, and it can be used to discharge either plain water or a Class A foam solution. Cellar nozzles are especially designed to be used on basement fires that are otherwise inaccessible for standard firefighting operations. They're sometimes referred to as basement nozzles or distributors. So this is one form of a broken stream. Cellar nozzles mostly consist of a play pipe that contains a 90-degree bend and a swivel inlet at one end and a circular or spinning nozzle head at the other. It may or may not have a shutoff valve on the play pipe. If the nozzle does not have an integral shutoff valve, inline shutoff valve should be placed at a convenient location back from the nozzle itself. Cellar nozzles can be used primarily by lowering them into the fire area through holes cut in the floor or other suitable openings. Prior to lowering the nozzle, use the tool to probe the opening and ensure nothing will obstruct the water stream. They may also be used to attack attic fires through holes made in the ceiling. Piercing nozzle is commonly used to apply water to areas otherwise inaccessible to water streams. They differ from cellar nozzles in that they eliminate the step of first creating a hole for the nozzle. Piercing nozzles create their own hole and then discharge water onto the fire. The piercing nozzle is generally 3 to 6 feet long or 2 to 3 meters, hollow steel rod that's 1.5 inches or 38 millimeters in diameter. The discharge end is usually hardened steel point that's suitable for driving through masonry, metal, plywood, sheetrock, or other wall and partition assembly. The point contains a series of small holes through which water or foam solution is flowed in all directions. Opposite the pointed end, or the pointed nozzle, is the driving end. This is driven with a sledgehammer to force the point through obstruction. Here's an example of a piercing nozzle being driven through a wall to access a fire. Piercing nozzles are attached to some aerial devices, most commonly those on ARF apparatus. And so this is one example of a remote reach ARF piercing nozzle. It's common to equip a piercing nozzle with one pre-connected attack line on a pumper, which allows quick deployment on fires such as engine compartment fires on automobiles or structural fires in metal wall buildings. Chimney nozzles are another form of broken stream nozzle, and these are used to attack chimney flue fires. The nozzle is a solid piece of brass or steel with numerous very small impinging holes around the circumference and are designed to be placed on the end of the booster hose. The hose and nozzle are then lowered down the entire length of the chimney and quickly pulled out. With chimney nozzles at a nozzle pressure of 100 psi or 700 kilopascals, the chimney nozzle generally produces only 1.5 to 3 gallons per minute or 6 to 12 liters per minute of water in a very fine misty fog cone. The mist from the nozzle immediately turns to steam and chokes the flue fire, as well as loosening soot on the inside of the chimney. Water curtain nozzle is another type of broken stream. This is a nozzle that produces a fan-shaped stream that acts as a water curtain between firefighters and the fire or combustible material that may be present. Some water curtain nozzles are designed for inline, so they have both an intake fitting and a discharge fitting. This allows several water curtain nozzles to be placed at intervals along the line. The top of the water curtain nozzle contains a semicircular head with small holes around the circumference that create a fan-shaped stream of water. Modern North American fire service rarely uses water curtain nozzles today. The water curtain is effective in absorbing only convected heat from a fire. Radiated heat is transmitted through the water curtain and can be reduced only by placing water on the exposure itself. They're still commonly used in Europe and other parts of the world, however. The water curtain between the fire and combustible material is not as effective as the same amount of water flowing over the surface of the combustible material itself. It's better to direct fire streams onto exposed surfaces. Make sure to angle water curtain nozzles so the water cascades down one side of the exposure being protected rather than spraying straight up into the air. Here are some review questions. What characteristic of broken stream nozzles can make them more useful than fog nozzles? See page 263 of your text. Next, which broken stream nozzle may be used on attic fires? That's on page 264 of your text. Next question, how does a piercing nozzle differ from a cellar nozzle? That's on page 264 of your text. Learning objective 4, we will demonstrate how to calculate nozzle pressure and nozzle reaction in various types of nozzles. Nozzle reaction is the force that pushes back on firefighters handling hose line when water is discharged from a nozzle at a given pressure. The greater the nozzle discharge pressure, the greater the resulting nozzle reaction will be. It sets practical limits on discharge pressure for both handline and portable master streams. The nozzle reaction does. If firefighters or portable master stream devices cannot handle nozzle reaction from excessive discharge pressure, the likely result will be loose nozzle or hose that can injure or kill personnel in its proximity. Some practical working limits for velocity of fire streams are from 60 to 120 feet or 20 to 40 meters per second. Equate this to measurement of PSI or kilopascals. Regardless of type or design, most nozzles operate within these velocity parameters when discharge pressures range from 25 to 100 psi or 175 to 700 kilopascals. Traditional fog nozzles are designed to operate at a pressure of 100 psi or 700 kilopascals. This is the upper limit of the manageability scale. Low pressure nozzles, just to remind you, are used on all incidents by some jurisdictions, designed to flow rated capacity at 50 to 75 or 350 to 525 kilopascals and can flow the same amount of water as a standard nozzle, but the reduced nozzle reaction will make the hose easier to handle. Fog nozzles can handle higher nozzle pressures because their inner workings dissipate the nozzle reaction to a certain extent. Solid stream nozzles are essentially tapered, straight pipes with no internal obstructions of the airway. Solid stream nozzles produce more nozzle reaction, obviously, than fog nozzles. The rule of thumb for handline solid stream nozzles is 50 psi or 350 kilopascals. The nozzle pressure may be raised to no more than 65 psi or 455 kilopascals without becoming unmanageable. Above this, solid streams become increasingly difficult to handle. A portable master stream device equipped with a solid stream nozzle should not be operated above 80 psi or 560 kilopascals unless the manufacturer of the device approves it. Some manufacturers will specify a lower nozzle pressure. Exceeding the maximum rated nozzle pressure on aerial devices could cause nozzle reaction that damages aerial device. Determining the nozzle reaction from a given hose layout is not something the driver operator or other fire protection professional do on a fire scene. Calculations are almost always limited to pre-incident planning and development of SOPs. So we're going to show you the equation for calculating nozzle reaction for a solid stream nozzle. This is US customary or imperial system. So here's your formula. NR equals 1.57 times D squared times NP. And this is really straightforward. NR is nozzle reaction in pounds. That's what you want to find out. 1.57 is your constant. D is the nozzle diameter in inches, and NP is the nozzle pressure in PSI. Here's an example in US measurement. Determining the nozzle reaction from a 2.5-inch hand line equipped with a 1.5-inch tip operating at a nozzle pressure of 65 psi. So we take here's your formula again. Under the word solution, the first line is your formula again. So NR equals 1.57 times diameter squared times NP, which is nozzle pressure. So your constant times your diameter squared times your nozzle pressure gives you your nozzle reaction. Next line, you plug in the values. Nozzle reaction equals 1.57, which is your constant, times 1.5, which is your tip opening squared, times 65, which is your pounds per square inch. So the nozzle reaction, you factor that out and you get nozzle reaction equals 1.57 times 2.25 times 65. So you multiply those together and your nozzle reaction is 229.6 pounds. Very straightforward. But you can see why you wouldn't have time in a fire scene to sit there and calculate it, which is why this is relegated to the realm of pre-incident planning and SOPs. Here's another example. Determine the nozzle reaction from a detachable ladder pipe that is attached to an aerial ladder and is equipped with a 2-inch solid stream tip operating at PSI. Well, you're still trying to figure out nozzle reaction, so no matter what type of nozzle you're using, the formula is going to be the same. So again, your formula is nozzle reaction equals 1.57 times diameter squared times nozzle pressure. Next line, you plug in your values. Nozzle reaction equals 1.57, your constant, times 2 because it's 2-inch stream tip squared, times 80 because it's 80 psi. You factor that out. Your next line gives you 1.57 times 4 times 80, and you multiply those together, and your solution is nozzle reaction is 502.4 pounds. This is equation 11.2b, which is calculating nozzle reaction for solid stream nozzles in metric. Same formula, just in metric. So your formula is NR, nozzle reaction, equals 0.0015, that's your constant in metric, times diameter squared times nozzle pressure. So here's an example in metric. Determine the nozzle reaction from a 65 millimeter hand line equipped with a 38 millimeter tip operating at a nozzle pressure of 455 kilopascals. It gives you your formula here under solution. Here the first line is your formula. Nozzle reaction equals 0.0015 times diameter squared times NP, which is nozzle pressure. Next line, plug in your values. Nozzle reaction equals 0.0015, that's your constant, times 38 squared because it's 38 millimeter tip, times 455 because that's your nozzle pressure, 455 kilopascals. You factor that out and on the next line and then multiply those together, and your solution is nozzle reaction equals 986 kilopascals. Here's a second example in metric. Determine the nozzle reaction from a detachable ladder pipe that is attached to an aerial ladder and equipped with a 50 millimeter solid stream tip operating at 560 kilopascals. Again, your solution, under solution you get your formula, which is nozzle reaction equals 0.0015, your constant, times diameter squared times NP, which is nozzle pressure. So the next line, nozzle reaction is 0.0015 times 50, it's a 50 millimeter tip, squared times 560 because your nozzle pressure is 560 kilopascals. You factor that out on the next line and you get 0.0015 times 2500 times 560. You multiply those together and your nozzle reaction is 2100 kilopascals. You can calculate the approximate nozzle reaction from a fog stream nozzle, whether it is a handline or master stream appliance. At best, it is only an approximation. Each nozzle reaction will vary depending on the nozzle's design. Here's an example. Calculating nozzle reaction for fog stream nozzles. We did solid stream, now we're doing fog. This is equation 11.3a from your book. And so for US customary or imperial measurement, you have NR, which is nozzle reaction, equals 0.0505, which is your constant, times Q, which is total flow through the nozzle in gallons per minute, times the square root of NP, which is your nozzle pressure in PSI. Here's an example. Find the nozzle reaction of a 1 3/4 inch hose line with a high-rise fog nozzle flowing 175 gallons per minute at 75 psi. The solution is as follows. Here's your formula again. Nozzle reaction equals 0.0505, which is your constant, times Q, which is your flow rate, times the square root of NP, which is your nozzle pressure. So nozzle reaction equals 0.0505 times 175, because it's 175 gallons per minute, and the square root is of 75 because it's 75 psi. That's your nozzle pressure. You multiply those together. After you take the square root of 75, you get 8.66. So on the next line, you have your constant times your gallons per minute times the square root of your pounds per square inch, your nozzle pressure. And when you multiply those together, your nozzle reaction equals 76.5 pounds. This is the equation 11.3a, which is calculating nozzle reaction for fog stream nozzles in metric. So the formula is going to be the same, just different values because it's metric. So nozzle reaction equals 0.022563, which is your constant in metric, times Q, which is your flow rate, times the square root of NP, which is your nozzle pressure in kilopascals. Here's an example of this formula in metric. Find the nozzle reaction of a 45 millimeter hose line with a high-rise fog nozzle flowing 700 liters per minute at 525 kilopascals. The solution, under solution, you have your first line, which is the formula. Nozzle reaction equals 0.022563, which is your constant in metric, times Q, your flow rate, times the square root of NP, which is your nozzle pressure. The next line, you would just plug in your values. Nozzle reaction equals 0.022563 times 700, because you're flowing at 700 liters per minute, times the square root of 525, which is 525 kilopascals. On the next line, you factor out the square root, and you get 0.022563 times 700 times 22.9. That gives you a nozzle reaction of 362 newtons. Okay, a couple of review questions. First, which fire hose nozzle produces the most nozzle reaction? That will be on page 268 of your text. Next question, when are calculations for the nozzle reaction from a given hose layout typically determined? That's on page 269 of your text. Class, as always, I always thank you for your attention, and I sincerely mean it. Now, in this chapter, there's a fair amount of technical material that's covered. Make sure to contact your instructor if you have any questions about anything. Thank you again, and we will meet for chapter 12.